Hey, good morning, everybody. Hey, we are sitting here and about to record the week 3 lecture 1, and this is going to be on two-dimensional motion. So 2D motion. So, you guys, I'm going to kind of talk about this, but we're obviously doing this with students, which is going to be Tuesday, second period. So I'm going to probably be directing more of my attention towards them. So as we'll go, so just kind of follow along. And I am going to try to get rid of some of this glare. Hold on a second. No. All right, so not quite working. All right, so you guys, in two-dimensional motion, okay? So if we have the path of an object that goes something like this, right? So not in a straight line, not purely in the x direction, not purely in the y direction. So if we want to know what that vector is in the beginning, okay, then we can kind of draw a vector like so, and let's say it's something like this, okay? So this is going to be my initial position, the initial position. So if you guys will notice there that this right here is, okay, I didn't put X and I didn't put Y, I put R, which is kind of like the hypotenuse. So what we really have here is we kind of have an X direction and a Y direction, which is going to make up that vector. Okay, so it's essentially, we're taking any old vector and we're changing it into a right triangle. So remember, X and Y are always going to be at right angles, as is I and J. So any vector that I write, we can break apart into I and J, which I will do in a minute. Now, if we essentially go over here, and now we have a vector and now here is our final. Now we obviously know that it is going in a different direction. Not only is it going in a different direction in the X and also the Y, okay? And again, we can break that into this and this, okay? And so if we want to know what our delta R is, how much did it change by? How much did it change by? Okay, so we know from before, we're going to say R final minus R initial, right? R final minus R initial. Okay, so we're going to take, now remember, these vectors, we can pick them up and we can move them. We can pick them up and we can move them. Okay, and when we do that, we have to keep the same length of our vector and we have to keep the same angle. Okay, so I'm going to try to do this. So if I have this, I can kind of put it down like that. Okay, and this would be R final, something like that. And now we're going to take this R initial, okay, and we are going to and this would be R initial. Does that make sense? Okay. Now, what we could do here is we are going to if we say our final minus our initial, if we start here, I'll use a different color here. This vector right here would be our final plus our initial, right? And we don't want that. We want our final minus our initial, okay? So a reminder back to lecture or week 2, lecture 3, in order to make our initial negative, we're just going to have it go in the opposite direction. So essentially what we've got here is we're going to have it go. So this is negative r initial. We have vectors here. So now we are going to have this right here. Let's do it in black. So this is delta R. That is delta R. Does that make sense? Okay. Now, another way we can look at it here is if we say, R initial and R final, R initial and R final. Okay, like that. So notice that they are both starting head to head, tail to tail. Okay. So what's going to happen here is essentially what we have here is our delta R. Okay. So this vector is our delta R, and that vector is our delta R. So we can actually see that these two are the same delta R's. They're the same delta R's. So if we, and kind of what I'm trying to say here, if we both start a vector and with the tail to tail, tail to tail, as opposed to when we normally are going to graphically add things, we're going to go the tail of the second one to the head of the first one. Okay. But if we know that this is going to be our R initial and this is going to be our R final, we can kind of draw this line right there, and that is going to be our delta. Okay. All right. So let's take a look. Let's take a look at this sort of analytically. So we're going to take these same two vectors, okay, and we're going to give them numbers. Okay, so what I've got here is about 2.5 and about 4.5. Okay, so my Ri is going to be 2.5i and 4.5j. Okay, so what I've done is I've just measured it. I've just measured that. Okay, and now I'm going to measure this one, which is going to be 4.5 and about 2.5. Okay, so my R final is going to be 4.5 and then negative 2.5. Okay, so I went positive 4.5 and I want negative 2.5 J. Guys, are you guys with me? Okay, now, if I want to subtract these, okay, what happens to the I and j? What happens to the I and j if I subtract? If I'm subtracting this vector, how do we make this vector negative? And the way we do that is we're just going to change the sign, okay? So now they're both positive, okay? So they're both going to become negative. If you had a positive negative, then the signs just switch, okay? And obviously, if they're both negative, then they're just going to switch. Now, now we can add those up, and we're going to have 4.5 minus 2.5, which is going to be 2i. And now we're going to have negative 2.5 minus 4.5, and that is going to be negative 7. Does that make sense? Okay, so our delta R is going to equal to 2i negative 7j. Okay, now if we look at this one right here, remember, this was our delta R when we did it graphically, okay? And now, if we, roughly speaking, we're going to get about 2. Draw this a little more. We're going to get positive 2, and we're going to get negative 7, okay? So this was plus 2 minus 7, okay? Now, we can see that if I did that more precisely, we would kind of nail it. But that is a pretty good sort of thing. So again, it doesn't matter if we measured this one, we would go over 2 down 7, over 2 down 7. Yeah.
For example, on like word problems and things, with the problem itself tells how much to measure. Because usually with the food.
Yeah, and mostly what's probably going to happen here is that, and I'll go over that in just a second. Okay, is you're, as opposed to measuring vectors, they're going to give it to you in the i's and j's. Okay, so that we're going to be doing it more analytically anyways. Okay, now. When we do it graphically, it kind of is that quick sort of check. Are we in the ballpark? Are we in the ballpark? So, for example, if we have a delivery person, let's say an Uber driver, and they've got 3 deliveries. They've got 3 deliveries to make, right? So their first one, let's say, is going to be 1.5 north and 0 east. Okay, so if we do kind of a graphic here, okay, and we say 1, 2, 1, 2, we're going to basically, their first vector is going to be like that. So this is vector 1, right? And then they are going to go, let's say, 2.5 miles east, 2.5 miles east. Okay, so the second vector is going to be 0 north and 2.5 east. And 1, 2, 3. And now we're going to have this vector like so. And now the third vector is going to be, let's say, about 2.1. 2.1 southwest. 2.1 southwest. Okay? Now, if we go 2.1 southwest, okay, Now let's think about this vector of 2.1. Okay, how far south do we go? And how far west do we go? Okay, now if we say, and I should say southwest, if this is southwest and this is south, what angle is that? Okay, if we go south and west, this is southwest. What angle is that? What's that? 45. It's going to be 45, right? Because if we think about a compass, right? North is here, east is here. That's going to be a right angle because we've got 360 degrees all the way around. And if we go halfway, northeast or southwest, that is going to bisect that 90-degree angle. So this is 45. All right, so if our hypotenuse is 2.1, then what are each of the legs going to be? Okay, and now we're going to say a squared plus b squared is equal to c squared, right? Except in a 45-degree triangle, okay, it is going to be a squared. So we're going to have 2a squared is equal to c squared. 2a squared is equal to c squared. Okay. And we know that c is 2.1. Okay. So we're going to have 2.1 squared is equal to 2 times a squared. Actually, we can just take the square root of everything, and then we're just going to get the square root of 2. The square root of 2a, is going to be 2.1. Okay, so if we multiply, or 2.1 divided by the square root of 2, 2.1 divided by the square root of 2, 2.1 divided by the square root of 2 is going to be 1.48. 1.48. Am I still on camera? Okay, barely here. So I'm going to move this. 2.1 divided by the square root of 2 is going to be 1.48. Let's call that 1.5. Let's call that 1.5. Okay? But that's 1.5 this way and 1.5 that way, down and to the left. Okay? So when we put it in here, okay, we are going to say negative 1.5 north and negative 1.5 east. Okay, now negative 1.5 north is the same thing as south, and negative 1.5 east is the same thing as positive 1.5 west. Are you guys with me there? All right, now, you guys, there's probably an easier way. To figure out this the fact that these are 1.5s, okay? And they're the fact that if you knew what the angle was, okay, but it wasn't 45, right? Then we can just say 2.1 cosine 45 and 2.1 sine 45. So if I say 2.1 cosine 45, I'm going to get the same 1.48. And when I go 2.1 sine 45 is also going to be 1.48. So it's kind of our job there to realize that we're going negative, negative, or south and west, right? All right, so now we add these together, okay? Now, just to keep them the same, I'm going to put that negative back in there, and I'm going to say that negative back in there. And now we're going to have 1.50, negative 1.5, so that's going to be 0 north. And we're going to have 0 plus 2.5 minus 1.5, which is going to be 1.0 east. Okay, now, if we looked at this graphically, and again, this graph is not very precise here, but I went north 1.5, I went east 2.5, and then I went 2.1 to the southwest. We can see that how far am I away from my original starting point? And I'm about 1 mile. Did I use miles? Okay. We had about 1 mile to the east, which is 1 mile to the east. Okay. So doing that graphically gives you a clue as to how close you are. So if you sketch that out, okay, when you're trying to kind of get an idea. So in a question, it might just give you these components. And when we go typically in the X direction and the Y direction, if we have something that is going both, there's going to be a lot of times where we just do it in the I and the J. Okay, so I'm about to write all those kind of equations, our 4 equations in the X direction, in the X and Y directions at the same time. In the X direction and Y direction at the same time. Okay, so let us kind of look at equation number 1, delta V. Now that's the average velocity. Remember that bar over that is going to be average. The arrow over that is going to be a vector, okay? And that's going to be equal to delta R over T. Delta R over T, okay? And that is going to be V final minus V initial over 2. Make sense? Okay, but remember, this is going to be delta this is going to be the change in the I direction. So we could say delta R in the I direction and delta R in the J direction over time, which would be equal to V final in the I plus V final in the J minus V initial in the I minus V final in the, VI in the J all over 2. Okay, so what we've done there is we just combined the I's and J's in there. Okay, so if we go to equation 2, now we're going to say V final, okay, which would be V final in the I plus V final in the J is going to equal to V initial I plus V initial J plus A in the I plus A in the J times T. So we can see we're getting those components in the I and J. And it makes it look super complicated, right? Okay. And although we can do that, I would say in your head, if you kind of separate them out into the x direction and the y direction, it's going to kind of sort itself out. So when you see something sort of complicated like that, and I am going to give you on problem set number 2, and that I'm trying to get to that question. Number 5, okay. It says a fish swimming on a horizontal plane has a VI that's equal to 4I plus 1J meters per second. If it says 4I plus 1J, and then in parentheses, and it's going to say meters per second, okay, since the unit is telling you meters per second, you know that's its velocity component, okay? So we can get into this equation number 3, and we could even do this x final is going to equal to x initial plus VIIT plus 1/2 AI t squared plus, sorry, we're going to say R final, and that is going to equal to y initial plus VIJT plus 1/2 AJT squared, okay? And these are all of the x or I components, and these are the j components. And then we can see that that would give us the hypotenuse. That would give us the hypotenuse that R final in the x direction and the y direction, or the I and j. Okay. Now, if we were to just kind of quickly say delta R like that, then we can get rid of these components. We can get rid of those components right there, because this is already saying the change, and then depending on where we started. Does that make sense? Okay. And then we would have V final squared is equal to V initial squared plus 2A delta R. Now you guys can imagine here that I could separate out these. I could say VII squared plus 2AI times x final minus x initial, and that would be in the I direction. And this whole thing is going to be plus the same thing in the y or j direction. So we'd have Vij squared plus 2aj times y final minus y initial, which would be in that j direction. And so again, we have those same things. It just looks much more complicated. It just looks much more complicated than we would have otherwise. So, makes sense? Looks confusing? I think it looks confusing. Okay, so part of that, okay, and we're about to do an example, and we're going to do an example of a projectile, okay? Now, last week, I forget what day it was. I think it was the Thursday where we had someone throwing an object off of the ground, off of a cliff, and one was throwing it down and one was throwing it up. So we're going to kind of do that the same way, except instead of them throwing it straight up or straight down, we're going to have them throw it at an angle, okay, which is also known as projectile motion. Projectile motion. And in that case, we're going to have both the X direction and the Y direction at the same time. Okay, make sense? Okay, so I am going to kind of start over here with this example. So we're, again, think about all that confusion that I just put up there, okay? And we're going to kind of simplify it here, okay? All right. So let's have a cliff here. Do you guys remember what the how tall the cliff was from last Thursday's 20? So we'll make it the same, 20 meters per second. And what was the initial velocity? Then when the object was throwing it down or up, what was that originally?
I thought it was
10. Okay, so now we're going to say the initial velocity is equal to 10 meters per second, except now we are going to have them throw it at an angle of 37 degrees. Okay, now you can imagine if we threw it at 10 degrees, at 37 degrees above the horizontal, you guys could probably see that it would kind of end up doing something like this. And whenever you throw something, kick something, launch something, shoot something, kick something, anything like that, and it's in free fall, okay, then it is going to form a parabolic curve. It is going to form that characteristic parabola. And why is that? Okay, so what we're going to do here is we are going to take and look at the equations, look at the same four equations. Instead of putting them all together, we're just going to do it twice, okay? So we're going to have the Y direction, and we're going to have the X direction. Okay, now this would be known as the J, and this would be known as the I from the actual direction that they're going, which is the unit vector notation. Okay. Now, what is the initial position? What is the initial position of the Y?
20.
It's going to be 20, right? So that's going to be 20. What is the initial position in the X going to be?
0.
It's going to be 0. Okay. And we could, again, think of that as a Cartesian plane. And in that Cartesian plane, we're at 0, 20. And what is our initial velocity? What is our initial velocity going to be? Now, 10 is at an angle. So I want to know how fast is it going upwards? And then in the X direction, I want to know how fast it's going in the X direction. Okay? So before, what we can say here is that VI is going to equal to 10 sine 37. Okay? That's going to give us the Y or the J direction. Okay? And 10 sine 37 should give us something about 6. Okay, so we know, and that would be in the eye here. So we know that we've got 6 meters per second. And now if we do so now we've got 10 cosine 37, 10 cosine 37, and that is going to be 8 meters per second. 8 meters per second. Okay. How did I do that in my head so quickly? You guys, that is a 3, 4, 5 triangle. That is a 3, 4, 5 triangle, or it is a 6, 8, 10 triangle, a 6, 8, 10 triangle. Okay, so I know that. I made up the angle because I know that the angle of a 3, 4, 5 triangle is 37 and 53. Now, not exactly, but close enough. So when I give you a 3, 4, 5 triangle, you can assume that this is 37, and then obviously this is going to be 53 degrees. So if you see 53 degrees or 37 degrees, you should be thinking in your head, hey, this is a 3, 4, 5 triangle. And that way, and usually when I do examples on the board, I'm going to use some of those triangles like I did a minute ago when we used a 45, okay, or 30, 60, 90, or a 5, 12, 13. So you will see me use those, and you'll see those in a lot of examples. All right. So now we don't know what our final velocity in the y direction, and we don't know our final velocity in the x direction, or do we? Now we have acceleration. You guys, what is the acceleration in the y direction if we throw something off that cliff? 9.8, and it's 9.8 now, 9.8 down because that's gravity. Okay, so now we're going to say negative 9.8 meters per second squared. What is our acceleration? What is our acceleration in the x direction? This right here is a very obvious answer that is not so obvious. Okay, but afterwards you'll kind of get that. Gravity is only acting up and down, right? So gravity is not acting in the x direction. Okay, so there is zero acceleration in the x direction. Now, actually, there would be some negative acceleration that is due to air resistance. Okay, but it's very complicated because that air resistance is proportional to velocity. So as it goes faster and faster, that acceleration goes up. So for now, we are going to ignore air resistance. So that means there is zero acceleration. There is zero acceleration. All right, and now we don't know the time, and we don't know the time. Okay, so now x direction and y direction. What is the difference? What is the difference between the time in the x direction and the time in the y direction and the time in the x direction? What's the difference in time if this object is going to go up and come down? Does it take any longer to go up and down than it does to go left and right? And again, obvious answer. That's not so obvious. And you guys might have already be thinking about the obvious answer. You guys, this object is moving. Its x direction and y direction are moving simultaneous, right? So this time, they're equal to each other. Okay, the time here is equal to the time there. Because it doesn't separate and go up and down and left and right separately. It's moving together. We're just describing it in the x direction and the y direction. Okay, so the time is the same, and that's the key. That is the key to these problems. The key is time in the x is equal to time in the y. It's the same. All right. Now, I didn't specifically, you guys, I did not specifically ask you what the question was asking here. And I want to know, what is the final velocity? And I think that right there was what I asked you in last Thursday's question of the day. So that's kind of where I was headed. So now we're going to say V final is equal to V initial plus AT. Now this is all in the x direction, okay? So we could say I as well. Okay, that just gives us our direction. Now, our initial velocity was 8 meters per second. What is our acceleration in the x direction?
0.
It's 0, okay? So what is our final velocity in the x direction? Okay, obvious, but not quite so obvious because this is all new, okay? In the x direction, velocity is constant, okay? There is no, and we'll get to forces next unit, but there are no forces to make it speed up or slow down, okay? So in the x direction, it stays the same. In the x direction, it stays the same, okay? Now, we can therefore describe the time, okay? And we can say velocity, okay? Let me see here. So if we go delta y is equal to v I t plus 1/2 a t squared. Okay, this is our delta y. Okay, so what is our change in y? Okay, so our change in y is going to end up being negative 20, right? Okay. So negative 20 is equal to 6t minus 4.9 t squared. Are you guys good there? All right. Now you guys can probably see here, just like it was last Thursday, this is going to end up being a quadratic, okay? So I'm going to rewrite this, and I'm going to say negative 4.9 t squared plus 6t plus 20. Now, and that's going to equal to 0. And now what I can say here, and I am just going to put this into a quadratic equation problem solver in my computer. Okay, and I'm going to get a time of 2.7. Time is equal to 2.7 seconds. 2.7 seconds. So now there's a second time, which is negative 1.5, but that negative 1.5, it doesn't make physical sense. All right. So now what we can do is, and I'm going to sneak over here, I'm going to say V final in the y direction is equal to V initial minus 9.8 t. 9.8 t. I should say plus AT. Now when we plug in numbers, we're going to have positive 6 minus 9.8 times 2.7. Okay? And we are going to say 6 minus 9.8 times 2.7, and that is going to equal to negative 20.5. So let's just call it V final Y. Let's just call it negative 20 meters per second. All right, so what is our final velocity in the x direction? Same as the initial. This was just 8. Now, we can see here as this comes down, we're going to have two components. We're going to have a positive y, a positive x, and a negative y. Okay, so if I kind of take that and bring it over here, we're going to go, it still has 8 meters per second, but it started up here and it ended up being negative 20 meters per second. So what is our overall velocity? And now what we can do here is say Pythagorean theorem, and we can say 20 squared plus 8 squared is, and then we take the square root of that, and we should probably get something about 21.7, I'm guessing.
21.5.
Dang it. 21.5. Okay. So our velocity, our final velocity is equal to 21.5 meters per second. But remember, that is a vector. That is a vector, and a vector has magnitude, and our magnitude is 21.5. What direction is that? Now, as we've already pointed out here, okay, we know it's kind of coming down here. So how would we get this angle? And now we're going to use inverse tangent. Okay, and that inverse tangent is going to be negative 20 over 8. And using the calculator, I'm going to say inverse tangent of negative 20 divided by 8. And I'm going to get negative 68 degrees. Okay? So I have got 21.5 meters per second at negative 68 degrees. Now, that's from our standard position being 0 degrees. We could say 68 degrees below the horizontal, 68 degrees below the horizontal. Because if we had done the same question, except I had it go that direction, right? Because sometimes you could kind of draw it going in that negative direction. And regardless, if we did that, if you said negative, or if you had 68 degrees below the horizontal, then you wouldn't have to essentially add that 180 degrees, you wouldn't have to add that 180 degrees to get it to go in that direction. All right, so there's really two answers here. Our final velocity, we could also say, okay, and leave it in our I and J components, and that would be 8I negative 20J meters per second. So this is polar coordinates. Polar coordinates, which has the magnitude and the direction. Now, if we put it in our I and J format, or our component format, then we can just say that it is positive 8, negative 20, I and J respectively. And we could quickly, just as we did, we could solve for the magnitude, which would have been 21.5, and we could have solved for the angle like we did. So There are times, if I do not ask it specifically, you can give the answer in the I and J format. And there are other times that I will ask you for the magnitude and the direction. The magnitude and the direction. The magnitude is just the number. Is just the number. So just as we had 21.5 here as our magnitude, okay? This one right here, going back to the original, our magnitude here was 10, just the number. The direction is going to give us the angle. This angle was negative 68. This angle was positive 37. So don't get hung up on magnitude. It's just the number. It's the length of the hypotenuse, okay? So if we, in this case, it was velocity. In this case, it was velocity, okay? And you will see that we can do this. We can see how far it goes, and we can see how high it goes, and things like that. But that's just more of that example. But there you have it. That is, in essence, two-dimensional kinematics, two-dimensional motions, and we can kind of describe it in different ways. I think breaking it apart here is a good way to do it because it's less confusing. And recall that the key to doing this way is realizing that the time is the same in the X direction as the Y direction. Okay. All right. Hope that was helpful, and we will see you guys next time.